Hey guys, this short lecture is on radiation units and calculations. So there's lots of units and measurements and formulas associated with radiation, but fortunately all of these have very specific relationships with each other. So here's an example of all of those measurements, units, and formulas. We'll look at these all in the context of practice problems, but just a few things to point out. The measurement of exposure is actually a way of measuring the ionizations in air, and there's no special unit for that. We simply calculate it as the number of coulombs per kilogram. A related measurement is air Kerma. And air Kerma, instead of measuring the number of ionizations in air Kerma measures the energy of those ionizations in air. In fact, Kerma, that word, is actually an acronym which stands for kinetic energy released per unit mass. Air Kerma is measured in units of gray, and 1 gray is equal to 1 joule of energy per kilogram of mass. Once we start moving into tissues or matter, another measurement that we're concerned with often is the absorbed dose, represented by the letter D. Absorbed dose is also represented by units of gray, and again, the absorbed dose, or the gray, is equal to 1 joule of energy divided by kilograms. Also, equivalent dose is another dose that we can use to measure the biological damage from radiation in matter. So it's not just the energy in matter, but actually a representation of the biological damage of radiation in matter. Equivalent dose is represented in units of sievert, and the equivalent dose has a very special formula. The equivalent dose is equal to the absorbed dose, D, multiplied by a radiation weighting factor, which is something that we have to look up in a table. And then finally, the effective dose takes all of this one step further. Effective dose is also represented in units of sievert, and this represents biological damage and is actually used to estimate the stochastic effects of radiation, like cancer. Effective dose is equal to, again, a very special formula. The absorbed dose multiplied by a radiation weighting factor, and then also multiplied by a tissue weighting factor. So how do we use all of these measurements and units and formulas in calculations? Let's look at a few sample problems. Here's the first question. It's not really a mathematical problem, but it does make sure that we understand some definitions. So the coulombs of electric charge produced per kilogram of air is a measurement of which of these? There's a few key words here. Number one, we're talking about the coulombs of electric charge per kilogram of air. So immediately when we see the word air, we know we're probably talking about like exposure or air Kerma, or one of our measurements that relates to the quantification of radiation in air. And as it turns out, exposure is the answer, and that's because exposure is actually equal to the coulombs of charge per kilogram in air. This is actually our definition of exposure. Here's another question. Again, not a mathematical problem, but it is a conceptual issue. A radiation measurement describing the energy of ionizations in air is termed which of these? So the key word here is energy of ionizations in air again. Because it's talking about measuring radiation in air, we might be tempted to pick exposure. But remember that exposure is a measurement of the coulombs of electric charge in air, not the energy of those ionizations. When we're talking about the energy of ionizations, we're especially talking about air Kerma. Kerma, again, stands for kinetic energy released per unit mass. And when we measure Kerma in air, it's called air Kerma. And so we're not measuring the number of ionizations. Just like this question says, we're measuring the energy of those ionizations. Here's another question. This time we're going to start using some of our formulas. A radiograph of exposure results in 0.015 joules of energy absorbed by the liver. If the liver weighs 0.9 kilograms, what is the total absorbed dose to the liver? So we're supposed to measure the absorbed dose to the liver specifically. So the absorbed dose, D, is actually measured in grays, and remember, the gray is equal to 1 joule per kilogram. This is very convenient because this question actually gives us joules and the kilograms in which those joules of energy were absorbed. So now it's just a matter of plugging in the numbers. Our absorbed dose then is equal to 0.015 joules of energy divided by the weight of the liver, which is 0.9 kilograms, and that's going to equal one of our answers, which is actually A, 0.0167 gray. The key thing here is to recognize that we're measuring the absorbed dose, so we know we're measuring it in gray, and we know that the gray is equal to 1 joule per kilogram. And if we recognize all of that, we can easily calculate it by dividing the joules into kilograms. Here's another math problem. A radiation worker received a gonadal dose of 25 milligray over the course of a year. If 100% of this dose was from X-rays, what is the equivalent dose? The first thing we have to remember is we're not talking about absorbed dose anymore. We're not talking about exposure. This question is asking us to calculate the equivalent dose. So we should first write down the formula for equivalent dose, and equivalent dose is equal to the absorbed dose multiplied by a radiation weighting factor. And some of this information is given directly, some of it is not. Our absorbed dose is provided as 25 milligray, but what about our radiation weighting factor? Our radiation weighting factor depends entirely on the type of radiation that is exposing the person. In this case, it's X-rays. If we look this up in a table, we'll find that X-rays have a radiation weighting factor of 1. So this one's pretty simple. We simply take 25 times 1, and it equals, of course, 25. But what units should we use? When we calculate equivalent dose, we convert the milligray into millisieverts. We actually can immediately eliminate any answer option that uses the milligray, because equivalent dose is not measured in milligray, it's measured in millisieverts. So A could not be correct, D could not be correct, and so we know it's 25 millisieverts because that's how we measure equivalent dose. So the answer is B. Here's another question that makes things a little bit more complicated. The thyroid of a radiation worker is exposed to an absorbed dose of 10 milligray from an alpha-emitting radionuclide. Calculate the effective dose. So once again, the first thing that we should pay attention to is what kind of dose are we supposed to be calculating in the first place? And this question tells us very clearly that we're looking at the effective dose. So what is the formula for calculating effective dose? It's actually equal to the absorbed dose multiplied by a radiation weighting factor and then also multiplied by a tissue weighting factor. As usual, some of this information is provided directly and some is not. The absorbed dose we know is equal to 10 milligray, but what about the radiation weighting factor and the tissue weighting factor? If we look up the radiation weighting factor for alpha particles, it turns out that it's actually 20, and if we look up the tissue weighting factor for the thyroid, it turns out that it's actually 0.04. So we multiply all of that together, and we get an answer of 8 millisieverts. And that does happen to be one of our answer options, and that is B. Here's another question. During an AP scoliosis x-ray, the breast, the gonads, and the stomach of a person receive a dose of 3 milligray. What is the total effective dose? So once again, we're needing to measure the effective dose here. So we'll write down our formula for calculating effective dose. It's equal to the absorbed dose, which in this case is 3 milligray, multiplied by the radiation weighting factor multiplied by the tissue weighting factor. It's very important to remember that when we calculate effective dose, we have to remember that tissue weighting factor. So we can plug in some of the numbers. The absorbed dose is provided as 3. But what about the radiation weighting factor, and what about the tissue weighting factor? So this patient received a dose of X-rays. The radiation weighting factor for X-rays is simply 1. But then what about the tissue weighting factor? Because we're given 3 different tissues, the breast, the gonads, and the stomach. We can look all of those tissues up, and we'll find tables that show us the tissue weighting factors for each of those. And all we need to do is find them and add them together. The breasts have a tissue weighting factor of 0.12, the gonads have a tissue weighting factor of 0.08, and the stomach actually has a tissue weighting factor of 0.12 as well. So we add all of those together, that gives us a total tissue weighting factor of 0.32. We do the math, 3 times 1 times 0.32, gives us a total effective dose of 0.96 millisieverts, and so the answer is C. Here's the last question. This one's just a little bit trickier. An accident in a nuclear facility results in a whole body absorbed dose of 56 milligray. what is the effective dose? So let's write down our formula for effective dose one more time. Effective dose is equal to the absorbed dose multiplied by a radiation weighting factor multiplied by a tissue weighting factor. So our absorbed dose is given directly as 56. We're not given what kind of radiation this is. So for this question, we're just going to assume it's X-rays, which have a radiation weighting factor of 1. But then what about this tissue weighting factor? The easy thing about this question is actually it's a whole body exposure. So we don't have to worry about adding up different tissues. It's just all of the tissues of the human body. And when you add together all of the tissues of the human body, it actually gives us a total tissue weighting factor of 1. And so this one's very easy. We take 56 times 1 times 1. That gives us 56 millisieverts. So the answer is A.